you are watching this video, that means that I must be gone today, or maybe you were gone. Either way, I'm glad we're here, and it is 5-11. Yay, let's go ahead and get started. 5-11, this lesson is kind of lengthy, so be prepared for that, but also we'll be taking breaks in between here. This one is talking about walking rates. So student 1 walks at a constant rate of 3 feet per second. And here I am trying to zoom it in, but I keep writing either way. So student 2 walks at a constant rate of 5 feet per second. So it's the same amount of time, but they're actually going at a different rate. Now their rate is like the distance. Again, same amount of time, a very different distance. 3 feet versus 5 feet. Now I'm drawing it myself a mental picture of what this kind of looks like in my head. But we'll also be looking at a double number line down here, which is helpful. The elapsed time and the distance walked for each student vary together. So that's just like in 5-10, where we talk about quantities that vary together. So let t be the number of seconds elapsed, which is time, since students started walking, and d will be the number of feet the student has walked, which is the distance. When we're looking at these double number lines, I do like to go into them and label, and I write like a note to myself. I remember this saying 3 feet per second, and I notice at 1 second there's 3 feet, and then after another second, that student goes another 3 feet, making it 6, and then 9, and then 12, and it finalizes with 15 feet walked, and that's over 5 seconds. I would do the same thing for student 2, but I also, again, like to write my little notes to myself. So I know at the very end of this, it says 15 feet in 5 seconds. So I'm going through my mind thinking, are there some connections to be made here? When we go to student 2, it goes for 15 feet, so same distance, but that student is going quicker, right? It's not taking them 5 seconds. It's actually taking them 3 seconds. So they're going 15 feet in 3 seconds. So to go the same distance, student 2 actually goes quicker. It's interesting when you look at it in a double number line like that. So can t, the time, and d, the distance, be whole numbers? Can they be fractions or decimals? Think about this one as a class. Do you think that we could do distance with decimals or fractions? Can we do that? Can we do time in decimals or fractions? What do you think? Well, I know I've said before that you can have 2.5 minutes or 3 minutes, so that would make sense to have, fractions or decimals in time. Now for feet, I think you could go 2.5 feet. I don't think everybody walks an even foot amount when they walk, which would make sense. So I think they can be whole numbers, and they can also be fractions and decimals. So when we see today, it will not just be whole numbers. We're going to push ourselves, and we're going to be seeing fractions. And you see me try to write this, like, what the heck happened? I was simply trying to write, and it got all wonky. And if it was like a pen, it would look like it went just bloop right on it. So it can be fractions. So I could go 13.1 miles, right? That's a half marathon. I've done it before. It's really long. If you did a full marathon, it'd be 26.2 miles. So yeah, it can. When two variables are related, we can often think of one as a dependent and the other as an independent variable. The distance each student walks depends on the elapsed time. So d is the dependent variable and t is the independent variable. So if we were to draw this on a graph like this, and I labeled it the x going across and the y going up and down, so horizontal versus vertical, and I'm going to take my different color and dive right in here where the independent variable will be on the x and the y will be the dependent variable. We could, break down those words as far as what does dependent mean and independent. How are they the same? How are they different? I really have some technical difficulties, and it's for sure a user error on my part. We're going to use those, the numbers from those students, and we're actually going to make a table of both of them. So student 1, and I can go back and revisit it, where it says student 1 walks a constant rate of 3 feet per second. I can start filling this in. So after 0 seconds, they've walked 0 feet. I mean, that's obvious. And go back and check. They did say 3 feet per second, and I can look at the double number line and break that apart, and I can start filling it in. So you fill this in, and then let's check our answers. Hopefully yours says 3, 6, 9, 12, 15, 18. And for student 2, we're going to do the same thing, but we're not going to be using the 3. We're actually going to be using the 5, right? Because student 2 walks at a constant rate of 5 feet per second. So starting with 0, and then after 1 second, they go 5 feet, 2 seconds, they go 10 feet. Fill yours out, and let's check our answer. This should go 5, 10, 15, 20, 25. Now, I'm looking and I'm noticing on the right for student 2, they're going up by 5. On the left for student 1, they're going up by 3. And if I were to multiply my elapsed time by the distance, I would get my total distance. Now, the distance would be that main rate. When, like in student 2, they go 5 feet per second. If I multiply 1 by 5, I get my number. So, for student 1, if I wanted to find my distance, I would multiply the 3 by the 3 feet per second, and I would multiply that by the time and get my answer. So I'm drawing it on my rate table right now, where my 5 and my 3 are right next to my time, and now I get the distance. So if I wanted to know after 100 seconds, how far did student 2 go? Well, I would do 5 multiplied by 100 and get 500. I would do the same thing for student 1. If I wanted to find out how far they went after 30 seconds, I would do 3 multiplied by 30 and get my distance. And that's how you can really use this to your advantage to see rates. So how is each student walking rate related to the equation? The walking rate is the coefficient. Remember, it's that number in front of a variable. A coefficient of t. That main rate that we looked at for student 1, 3 feet per second. The 3 went in front of the t for time. Student 2 was 5 feet per second. The 5 went in front of the t for time. 5 multiplied by the time gives me the distance for student 2. So we have some grids on the next page. I'm going to show you how to graph them, and I will be going back and forth, but let's start with student 1. Now I know it's 0, 0, obvious, for the elapsed time, but I can go back and check where it said after 1 second they went 3 feet. So I'm going to go over to the right to the 1, and I'm going to go up 3. I go over to the right to the 2, and then I go up to 6. I'm going to do this until I reach 5, and I should be at the 15 by the time I get to the 5. Now if I multiply the seconds elapsed by the number 3, I will get the feet walked, or the distance. For student 2, I go through the same process, and I would be graphing it, oh, I went too far. I would be graphing it for the number 5 multiplied by our seconds or time. So you try this one, and let's come on back. If you did this correctly, which I'm sure you did, if you went over to the 1 to the right, you would go up 5. To the 2, you'd go up 10. To the 3, you'd go up 15. To the 4, you'd go up 20. And to the 5, you'd go up 25. And I can connect that with a line. Graphing, we've been doing since Unit 1, and it's fun to see everything build on each other, so we can't just let this go out of our brain just for fun. So I'm going to write on a note to myself, student 1 was 3 feet per second. So that means at the 1 second, I should be at the 3. Student 2 was 5 feet per second. At the 1 second, I should be at the 5, which I am. And each second, I'm going up 5 for student 2. And each second, I go up 3 for student 1. So there's a connection there. Well, now student 3. Oh, okay, so student 3 walks at a constant rate of 4 feet per second. Wow, so they go pretty far. I can draw a double number line to help me up there. Now, they must really love walking. It's kind of weird because I don't know if I've ever ran into students that really like walking this much, but good for them. They must be getting their steps in. Students here really love walking. So, after 1 second, student 3 went 4 feet. After 2 seconds, they must have gone 8 feet. After 3 seconds, they must have gone 12 feet. And after 4 seconds, they go 16 feet. And I'm writing and multiply by 4 by the time because that's how I'm getting my feet. I'm multiplying my time by 4 to get my distance. So how would I write this? So my distance is equal to 4t. So 4 multiplied by t. Just like I did at the bottom there. My distance and my time, they are related. And when I multiply my distance by 4, I get my, or my time by 4, I get my distance. And I really need to flip my numbers over there. So after 0 seconds, there has been 0 feet walked. That makes sense. And each of these I'm going to multiply by 4. Again, my time needs to multiply by my distance. And I already knew I was at 4 feet per second. So that's easy to do that way. So Seth and Kinsey, clearly best friends, want to know how far student 3 will have walked after 2½ seconds. So Seth says he can use a double number line to find the distance. Explain how he might do this. Now I'm going to draw something on here that helps me. And I'm going to draw it right in the middle. And it's between 2 and 3 seconds. Now, why do you think I put that in between 2 and 3 seconds? Just go ahead and dog your tables. Well, I did that because they asked for 2½ seconds. So in between there, which is between 2 and 3. It's actually directly in the middle because it's a half. And I could go through and make tick marks to make these into even smaller chunks, right? So in between the 1 and 2, there would be 1½ In between the 3 and 4, there would be 3½ In between the 0 and 1, it would be half. And I already know my answer must be between 8 and 12 feet. Now, I know that because if I'm cutting it in half to find the 2½ seconds, I can't say, well, they must have ran about 8 feet, or must have ran 12 feet, or really walked in this case. But I can't do that, and I really need to have an actual answer. So the entire time that I've been plugging in just multiply the 4 by 1, 2, 3, or 4, I'm actually going to be multiplying the 4 by 2½ And I'm doing 2½ this time because that's the elapsed time. Now, Kinsey, she's thinking my way with an equation, with that idea of, in number 8, we said distance is equal to 4t, so that's 4 multiplied by t. So we can substitute 2½ in for t. The equation did not change, but the number we put inside for the variables did, and that's okay. In fact, that's why those variables are there. They're there for us to substitute, plug in, whatever kind of lingo you want to use for that, and to solve. So when I do this, I already know my 4 needs to be over 1 because we're going to be multiplying fractions, and my 2½ is going to need to turn into what do you call that? Okay, improper fraction. It's been a while since we've used it, so if you didn't guess improper fraction, that's okay. To do that, I'm going to multiply my denominator by my whole number and then add my numerator. So right now it's 4 over 1 multiplied by 5 over 2. Once I get that set up, I will multiply straight across and I will get my answer. So 4 multiplied by 5 is 20, and 1 multiplied by 2 is 2. 20 divided by 2 is 10. So student 3 walks 10 feet in 2.5 seconds, which, if we looked at my estimation, it had to have been between 8 and 12 because we were looking at 2.5, just like our number line. Feels pretty good to do that. So this time we're going to plug in 3 1/4, or 3 1/4. I'm going to do the exact same thing. 4 over 1 multiplied by 3 1/4, which is 13 over 4. I solve straight across and I will get an answer of 52 over 4, and I can simplify that. How about you try number 11 and then let's come back and meet as a class. Number 10 is 13 feet, and number 11 I will set up the same way with 4 over 1 multiplied by 2 5/8. If I turn the 2 5/8 into an improper fraction, it is 21 over 8, and I multiply straight across and I get 84 over 8. I can simplify this, and I'm thinking, okay, how many times does that go in? 10.5 feet. So in 2 5/8 seconds, student 3 walks 10 1/2 feet. Wow, that's impressive. We're on to number 12, and now we have a student 4. Wow, these students love to walk, or actually maybe they just love to take their rate for their walking. Either way, this feels really above and beyond what normal things happen. So after 2 seconds, they walk 7 feet. So now I gotta think, what is halfway between 0 and 7? Well, I know if I had $7 and I split it into 2, each person would get 3 $1 bills, and then they would split 4 quarters, and so they'd have 3.5. So that must be in between the 0 and the 7. So this person, student 4, actually goes 3.5 feet per second. So even though we started with a rate of 7 feet per 2 seconds, or 7 feet every 2 seconds, we were able to figure out that you can find something even smaller and find the unit rate. A unit rate will feature the number 1. So per, that's the smallest you can go. So I can fill in the numbers that I have from my double number line in my table. After 2 seconds, student 4 goes 7 feet. After 4 seconds, student 4 goes 14 feet. And I know after 1 second, student 4 goes 3.5 feet. So I know 3.5 plus 3.5 is equal to 7, and if I add 3.5 to that, I'm going to find my answer for every 3 feet, which, remember, multiplication is repeated addition. So 7 plus 3.5 is 10.5, and for 5 seconds, I could do 5 multiplied by 3.5, or in this case, I will be adding 3.5 to 14 and getting 17 1/2. So unit rate is per 1. It's the lowest it can go, but not to 0. So I would write that the unit rate for student 4 is 3.5 feet per second. Unit rate will have a number per, or the word per, because we're going down to the bare number 1. This should also kind of make you think about how much money per gallon for gas. That's a unit rate. So in this case, it's 3.5 feet per second. I'm going to draw the 3.5 right next to my elapsed time, because our equation is 3.5 multiplied by t is equal to distance. So in number 15, when it says write an equation relating d and t, I will write d is equal to 3.5 t. 3.5 is the coefficient, and we're going to be multiplying by it. For numbers 16 and 17, can you go ahead and solve these in your group and then share, or you can send somebody up to the table, but to the whiteboard to share it. Use that equation in number 15. And here's it. Number 16 is going to be 3 multiplied by 3.5. I get an answer of 10 and 1/2, and it's also on my table. Now, wow, not only are we looking at a distance in, looking for a distance in fraction, but we're also multiplying this time it's in a fraction, 2.5 seconds. So 2 and 1/2 multiplied by 3 and 1/2, that's the same as saying 5 over 2 multiplied by 7 over 2, which is 35 over 4. I needed to remember to multiply across. And I end up pressing this crazy thing, like, how does this even happen? Who let this? Yeah, this is news to me. Little did I know this is what happens when you press the glasses in the right-hand corner. Who knew? Not this girl. That was kind of confusing. So 35 over 4, I can simplify into 8 3/4. 8 3/4 feet after 2 and 1/2 seconds. Holy cow, student 5. Okay, man, they just keep multiplying over here. So student 5 walks at a constant rate of 11 feet every 3 seconds. So that's not quite a unit rate. And making a note, these students really like to walk. But 11 feet for every 3 seconds is not a unit rate. It's just not. Now, why is it not a unit rate? Because it doesn't go down to every second. So we're going to write an equation relating d and t to student 5. First thing we need to do is find how many seconds they are, or how far they're walking in 1 second. We need to find the unit rate. Now I can draw myself a double number line and spread the 11 over 3 seconds. I can make a drawing dividing 11 into groups of 3, because that's going to tell me how far they can go in 3 seconds. I could also divide 11 by 3. Either way, I'm going to come up with an answer that helps me know what my unit rate is. So I'm going to divide 11 by 3, and I get an answer of 3 2/3. So student 5 walks 3 2/3 every foot. So, or every second. Yowza. So they walk 3 2/3 feet every second. Wow. Now, is this the farthest that these students that we've seen go? Could be. So try number 6 and number 6. Oh my gosh. Try number 19 and number 20 on your own, and then come on back using the equations that we already made. For number 19, I get an answer of 66 over 3, which is 22 feet. And I'm just plugging this 6 in for t, and I multiply 6 and 3 2/3. I'm going to do the same thing for number 20, but instead of 6, I'm going to multiply 3 2/3 by 7.5. So that's 11 over 3 multiplied by 15 over 2. I multiply straight across, and I will have a denominator of 6. And my numerator is going to be quite large because I have 11 and 15, so it's 165. You know, I will be simplifying this, and I divide it out. 6 goes into 16 2 times, and 6 goes into 45 7 times, and I have 3 left over, which is equal to 27 3/6, or 27.5. Now, number 20 is also similar to your exit ticket, but let's look at 21. Suppose a student walks at a constant rate of r feet per second. Label the double number line below for the student. So for 2 seconds, I'm going to write 2r, 3r, 4r, 5r, 6r, and so on. because the equation, the distance, is equal to my rate, so r, multiplied by time, right? In this case, it's multiplying by 1. And I notice that they don't tell us what the r stands for, so I'm just going to put a coefficient on it. So how can I summarize what I learned about distance, rate, and elapsed time, and how they're related to for motion at a constant rate? The distance walked is equal to the product, so multiplying the product of the elapsed time and the unit rate.